All right, let's talk about the glorious divergence theorem. Here it is in all of its tensorial glory. Here's what it's saying. Consider a tensor field Fi, a tensor field Fi in the domain omega, whose boundary is now S. So now S is not any surface, not just any surface. It's the boundary of the domain omega. It's the closed boundary. So it's a finite domain. And apply the covariant derivative to this tensor field of order 1. If it's not of order 1, the whole thing doesn't make any sense. I'll explain why in a moment. And now you have an invariant. Integrate this invariant. You have a number. Here's why this needs to be a tensor of order 1. If it's a tensor of order greater than 1, then even after you evaluate this covariant derivative and contract, there will be some indices. And that means there will be some variability from one point to another. And if you change your coordinate system, all the numbers will change. And as you know, it makes no sense at all to add two tensors that are not invariant, two tensors of order greater than 0 at different points, because they're essentially components with respect to different bases. So they cannot be added as components. Only invariant objects can be meaningfully added. But when they're decomposed, each with respect to its own basis, I'm stuttering a little bit because I'm thinking of analogies. So I have one. I'll give you one in a second. And that doesn't make any sense. Just like if you have a house worth $1 million and another house worth 1,000,000 rubles, you cannot add 1,000,000 to 1,000,000 and say it's 2 million of anything. You have to convert them to the same currency or to their value in gold or anything like that. But there needs to be a common basis for them to be added together. That's why tensors at different points cannot be meaningfully added. And because integration is all about addition, an integral only makes sense when it's applied to an invariant. And in order for it to be an invariant, this has to be a tensor field of order 1. So here we have an invariant. An invariant could be integrated. And the statement is that if F is sufficiently smooth, so of course all of our discussions apply to vector fields that are tensor fields that are sufficiently smooth, it equals the integral on the surface where that tensor field is contracted with a normal. So there is a beautiful geometric interpretation. Maybe one day we'll talk about it. I think my book speaks to it. Does it? Not sure. But there are plenty of books that do. This is called the flux. And of course, the whole interpretation of the theorem is that by studying the flux, you can capture the rate of change of something contained within the volume. Okay. So where does this come from? Well, it comes from this being essentially true in Cartesian coordinates in the plane or in three-dimensional space. So it's true in that setting, and in that setting, it's just a straight consequence of the fundamental theorem of calculus. I think that in my textbook, there's an exercise that asks you to derive the divergence theorem in the arithmetic setting, the arithmetic setting being just arithmetic integrals on fixed domains. So integration in the sense that you learned it in ordinary calculus, where it's an integral applied to functions, right? So of course, those courses typically don't talk about the geometric setting, where you have domains that exist without coordinate systems and so forth. But the two can be connected. The whole point of tensor calculus to connect them. I love the process of connecting the geometric views with arithmetic views. It's never more striking than it is when you talk about integration. But that's where you prove the divergence theorem in its purest form. And then it can be generalized to geometric domains. And then it can really be shown that this is true. And notice how tensor calculus is really central to the whole thing. It's really the covariant derivative. So the learning covariant derivatives was not in vain or in an idle hobby. It really is critical to anything that's geometric, right? It's the invariant derivative that we've been studying that figures in the divergence theory. One other word I want to say about divergence theorem before we switch to its application is that it works just as well on curved surfaces, where you would take the surface divergence. So on a patch, let's now call the patch S, and its boundary, its contour boundary gamma. So I use the letter capital U in my textbook, but I'm now beginning to like capital gamma a little bit better. The divergence theorem would look like this: an integral over the patch of the surface divergence. Now I will use a different letter, of some surface tensor field with surface components only, ds. That's an invariant. It equals the integral over the contour gamma, where you treat gamma as a surface the way we've been talking about surfaces, but now it's a one-dimensional surface of normal dotted, we're now using the letter G. G gamma, where this is the invariant integral of this invariant quantity. We're just a little bit ahead of ourselves because we never talked about surfaces embedded in surfaces. We've only talked about surfaces embedded in Euclidean spaces. Only when we were talking about the fantastic Gauss's Theorem egregium did I encourage you to think about the ambient space as being just a Riemann space. Well, here's another striking application of that. The reason why I'm comfortable using this notion without talking about it as much is because it carries over just perfectly smoothly. And everything can be developed by a complete analogy. You just have to pay slight attention to the ambient space not being Euclidean. But as far as normals and the curvatures and all of those things, everything works out. It's coming up, talking about surfaces within surfaces, and in this case, contour within surfaces and things like principal curvatures. So what is n alpha? N alpha is the normal to the contour. It's the normal to the contour that lies within the tangent plane. So I'm just inviting you to visualize it, right, and see the complete analogy between these two. This is actually a little bit more general, of course, but it works just as well. It's the same covariant derivative. So I think you should be having a really good feeling right now that all of these covariant derivatives and everything you've been studying, that may have seemed like a great organizational tool, some other positives, but generally perhaps slightly artificial. Well, it's not artificial at all. It's what, in applied mathematics, the covariant derivative are front and center of the entire subject. Okay, so now let me show you, without erasing the board because it won't take much space, 3 really striking applications of the divergence theorem. The last application will actually give you the perfect geometric interpretation of the mean curvature. Actually, I will erase, after all, just this, just this most important. All right, and now let's talk about those applications. Application number 1, to prove that given the domain and its vector normal n, a closed domain, if you take a closed domain and integrate over the closed surface the normal vector, the total integral of the normal vector, you can almost guess what it is, because the normal points in all the different directions. So if you keep adding all of those normals up, I think 0 is a good guess, and it's the right answer. 0. This will equal 0, but let's arrive at that answer analytically. And I just want to say it makes total sense that the answer is 0, because if you can think of this normal, if you submerge a body like this in some fluid, not fluid, because with fluid we think about gradient of pressure, but in midair, where we think of pressure as being constant, immerse an object like this in constant pressure field, then the sum of all the forces will be 0 because the pressure is equal on all the sides. So this body will actually not go anywhere. All of the forces will balance each other. Well, that means that the total force, you maybe times pressure. The pressure acts in the normal direction, is 0. Another good fact to prove would be that the total torque is 0. So we'll think about that. But let's prove that this is 0 by the divergence theorem. It's actually quite nice. Maybe you want to pause the video and see how you transform this expression in such a way that you can use the divergence theorem. But I'll proceed right now. So just write the normal as its component expanded with respect to the ambient space, with respect to the covariant basis. And now it's in a form where divergence theorem can be used, except we're using it from right to left. We're going from the surface integral to the volume integral. And of course, by the divergence theorem, this equals the integral over the domain of the divergence of this object. All right. And because the covariant derivative is metronylic with respect to the covariant basis, this object right here is 0 point-wise. So the whole integral equals 0. There we go. So I always found this to be quite a striking application of the divergence theorem. And notice how we proved it in arbitrary coordinates. This makes it a stone's throw away from actually being a geometric invariant definition. You have to be a total purist to say that this is not general enough because we use coordinate systems and we need a purer proof. I would think that's too much. So here's application number 1. Let me show you another application. Suppose once again you have a closed surface. The domain omega will now not play a role because we'll talk about surface integrals. And we'll talk about the total integral over the closed surface. We're assuming that it's closed. In a moment, we'll assume that it's not closed. Of the quantity normal. So we've already discussed the integral of normal. But what if we multiply the normal by mean curvature? What would this integral be? It's a fantastic question. Once again, can you think about a way to change this expression a little bit in such a way that the divergence theorem will apply? So maybe I'll pause for a moment. All right, but here it is. You recall that this quantity is in fact the covariant derivative on the surface of the contravariant basis. All right, so now we're actually going from left to right, but from the surface to the contour. So let me write divergence theorem. Of course, in a moment, I will say that there is no contour. So this is actually our second and third applications in one. For the second application, I will say, well, of course, there is no contour, so we have 0. But then we'll think about what happens if there is a contour. So in other words, if the surface is not closed. So here's the theorem we're using. So it'll be the normal times, well, contracted with whatever it is that the divergence was of. So it's integral over the surface of n alpha s alpha, excuse me, typo, over the contour, the gamma. And this, of course, if this is the component of the normal, of the in-plane normal, then this is the in-plane normal itself, because that would be the component with respect to the contravariant basis. So the whole thing, this beautiful expression of n of just the vector n. So this is actually our second and third applications at once. So if the surface is closed and there is no contour, there is no boundary, contour boundary, there is no integral, it's zero because there is no boundary. So in the case of closed surface, this is zero. This integral is zero. So not only is this zero by this volumetric, quote unquote, three-dimensional application of the divergence theorem, but this integral, the normal times mean curvature, is also zero by a completely different application of the divergence theorem, by the divergence theorem on the surface with respect to the non-existing contour. But what happens if the contour does exist? If there is, if it's just a patch? Let me draw, so this picture is quite adequate, but let me draw a nicer picture that will give you a very vivid interpretation of mean curvature B alpha alpha. And one of the reasons why I love this object so much. So here's a patch. I think I exaggerated it a little bit. Let me make it a little bit more subtle. Here's a patch. So you'll see what I'm going for in a moment. All right, so it's like a spherical cap, kind of. That's what that's what I was going for. That's S. A spherical cap, and this boundary right here, this boundary is gamma. And we're told that the integral of the normal times mean curvature, which perhaps points, in this case, it would be pointing this way, down. But I'll point it up, and I'll say that this is minus n b alpha alpha. I'll leave it as an exercise for you to think about why, when it's something's concave this way, n times b alpha alpha points downward. Remember how we always talked about how there you have a choice of normal, and depending on your choice of normal, mean curvature or the entire curvature tensor will have either one sign or the opposite sign. Well, when you put them in a product like this, it actually doesn't depend on the choice of normal at all, because they would both flip signs and the product would remain the same. So you can actually talk about it in absolute terms and not subject. This combination does not depend on the choice of normal, because both of these elements do and their product doesn't. Okay, so this relationship tells us that this integral equals the contour integral of this normal, surface normal. And I think it makes perfect sense, because the flatter the patch, the more these normals will cancel each other. In fact, if it's completely flat, then the integral of the normals will be zero by this theorem that we proved right here. But now when it goes from being flat to being slightly curved, these normals largely cancel, but there will be some net that doesn't cancel. So their sum, or in other words, their integral, doesn't cancel proportionally to what? To mean curvature. Where am I pointing? Right here. It's proportionally to mean curvature. So when mean curvature is zero, this integral is zero. So the extent to which this integral and all these norms doesn't vanish and all the normals don't cancel each other is due to mean curvature. So mean curvature is a measure of how much these contour normals don't cancel on a small patch. So that's a very vivid interpretation of mean curvature. That's very similar to Gaussian map interpretation of Gaussian curvature. So it's very valuable. And in fact, I've never seen it in any book. So it's completely elementary, I would say. But if somebody can point out a source where this is discussed in this form, or in any form, then please, other than my textbook, then please let me know. I would be very interested. So this is really it. We've talked about integration and the fundamental theorem of integration, which is the divergence theorem, and discussed 2.5 applications of the divergence theorem, one more striking than the next. So this completes our short introduction to integration. Thank you very much, and I'll see you next time.